Okay, so I think we can start. Yeah. Okay, so few words of introduction for Stefan. I actually have great memories of great chats with Stefan. I remember the first time we met, it was probably, I don't know, a humanoids talking about momentum control, if it was important to control the orientation or not, the role of the
Yes.
centroidal dynamics. So, yeah, it's with an extreme pleasure that I introduce Stéphane Caron. Stéphane has been working on many humanoids like HRP4 and HRP2 in France. And now he's also working with quadrupeds. So it's really somehow an honor for us to have Stéphane, an expert of motion control and planning for leg systems. Okay, I think that we can start. What do
Okay.
you think,
Take
Stefan?
three.
We can
Let's try
take
again.
three. Okay, let's try again. I already introduced you, so Stefan, the
Perfect.
floor is yours, and thank you very much once again for
Thanks.
giving us this talk.
Thanks a lot. Thanks a lot for inviting me, and I'm glad to be talking to you today. So I'll try to keep it not so long. There are way too many slides, and if I'm skipping something that you're interested in, feel free to raise a hand, and we can dive a little deeper. So I'd like to tell you about, well, two things. Motion control software, so something that we all do, and I hope that we can exchange some points on that. And then homemade robots, or at least robots that can be made at home or in research labs. So the reason why I want to talk about these topics, I mean, it's partially rooted in my experience. So I've worked with various robots in the past. Initially, I was working with humanoid robots like the HRP4 that you see on the left. But then I kind of diversified, at least in terms of morphology. I've worked with animal quadruped robots at ANYmal, and after that, I started some personal projects, and one of them was to build a wheel-legged robot, which you see on the right, and which is called Upkie. But we'll come back to that. So we have various robots, and I want to give you a highlight. I mean, it's not a highlight, but one implementation of what do we do in general. So, okay, we are doing research or we are working with robots, but well, in practice, it's usually the interaction of many things, and this is a bullshit simplification of many interacting complex things that I'm showing you here. But basically, at the forefront, we have people, people working on a specific topic. And this might range from the huge worldwide academic community to a local team. We develop software to implement our ideas, and this software runs on robots. And in this high-level simplification, to me, all the arrows are bi-directional, right? So you implement some software to run on the robot, but then it doesn't work on the robot, and you get feedback from reality. So you have to update your software. You also have to update your IDs when you're a group of people, et cetera, et cetera. So in that very general scope, today, I'd like to tell you about one particular implementation, one particular scope. For the people, the group of people working together, I want us to think about us as a global, worldwide community and how we can interact, especially with social networking collaborative environments like GitHub. Then for the software, I'm going to show you one particular implementation which tries to be split and shared as much as possible, but they're still work in progress. And then for the robot, we'll talk about the Upkie, the wheel biped robot in particular. But the floor is open to discussing other robots as you see fit. And so, without further ado, let me start with homemade robots or robots that we can make at home. So you probably have already heard or seen or manipulated or worked directly with one of these quasi-direct drive actuators that have hit the market recently in the latest year. So I'm going to show one brand, but there are really many brands that have reproduced the design. And I think that's one interesting technological innovation that came out recently and that can have benefits for us. So that's one thing we're going to talk about. And the other thing to keep in mind when we talk about homemade robots is the ability that we have now to prototype, to build things at home and with relatively efficient equipment like 3D printers. And these are two things. One of them is for prototyping, like you're not sure if something is going to hold or not. So you just build one iteration, try it, and then if it breaks, you have to, I don't know, increase the infill or increase some properties. So there is once the ability to iterate, and also the ability to repair if we break something. If the robot falls, then yeah, we're just going to print some new parts and repair the robot quickly. So these are two things that have, well, 3D printing has come for a longer time than the QDD actuators, but the combination of the two probably can help us move somewhere else on the spectrum of what we can do with building robots. This is just an overview of off-the-shelf actuators that we can find today. So I mentioned the quasi-direct drive, which is the design originally from Ben Katz of coupling a BLDC actuator with planetary gears. And it's widely commercially available. And it's interesting because it gives us a bit more torque. Sorry for that. I'm going to close that. A bit more torque than conventional BLDC actuators, especially if we want to build a mid-size, let's say a kid-size robots, and still be quite, get quite some peak torque if you want to do some explosive motion. And the price range also is quite interesting. There is also, it is possible to buy actuators based on the series elastic design. So there are some from Heavy Robotics. Not really, I haven't seen much on the homemade side, but it's also one option that we can use, and that fulfills roughly the same spectrum in terms of torque. It's a bit higher on the price range, but also it has some nice properties. So just to mention that it exists. Today I'm going to talk more in particular about so Upkie, which is one implementation of what we can do, and it's based on the MJ bus stack. So that's one company from the US, but from which you can order worldwide a whole range of components. And I mean, you basically have all the components you need to make a full-fledged robot, be it a quadruped or biped, wheeled, not wheeled. You build what you want, but you can basically order the actuators and the circuit boards. So the motor drivers, power distribution boards, which is a very simple board, and also a comms board that you can put on a Raspberry Pi to communicate with the CAN bus with the actuators. And so the example I want to talk to you about today is this wheeled biped, which is like, it's not minimal, but it's a small number of actuators with which we can test quite a number of things. And I was interested in balancing, so I made a balancing robot. It's only around 5 kilograms. So, it's a little bit heavy, but if it falls on you, it's really no problem. It takes quite a long time to print, but you don't have to do much. So between 30 and 40 hours to print with commercially available Prusa printer. And it has enough knee torque to stay fully crouched for as long as you want. You don't have to hit the thermal limits if you want to do that. And it has direct BLDC actuators in the wheels, because the wheels don't need a lot of torque. Even if you're climbing some 30, 40 degree slopes, you can use the robot for that. So it's just one example that fits the range of what we can do with these off-the-shelf actuators. It can also stay up and balancing for 3 to 4 hours without a problem, using, again, batteries that you can buy directly off the shelf. So that's one example that you can look at, just to illustrate that with commercially available things, we can actually build some prototypes pretty fast and test things. I also want to mention the starting of platforms to share 3D printed models. I'm not fully satisfied with what you can do on, so this one is printables. It's the one that comes with Prusa. There is also Thingiverse, which is more famous, so that people can share more efficiently 3D printed models the same way that we share code on GitHub. Although I must say, probably there's still room for improvement there, but it's quite convenient, and it gives us some ability to share. So why am I telling you about building robots today, homemade but not necessarily made at home? It's because also I think those are things that we can leverage in the research. So on the purely research side, it's quite convenient if we want to explore new morphologies. So you will see, for instance, there are a number of, if you go on the robotics side of Reddit, you will see people trying things. Many people try combinations of existing robots and technologies, not necessarily from legged robotics. So you can put a flywheel on a robot and see how it balances, for instance. Or even in research papers recently, we've seen combinations of wheels on the ground with flywheels for balancing. And that's made easier just because the stack is also growing thinner, and we got rid of a lot of the clutter that we had in our previous iterations. And then, of course, if you're focusing on one question, you can fit the robot to what you want to do. So if you're interested in balancing, you can make just an inverted pendulum. You don't need a knee, for instance. Or if you're interested in something that can jump or that can go on slopes on various terrains, then probably you start adding knees or you start adding things. But you can make a minimal robot for the question that you're interested in. And then from a research engineering point of view, so kind of bridging the way to, repeating experiments, making them more efficient, but still being connected to the research, we can have shorter development cycles in the sense that you have if the scope of the project is smaller, then you can have more generations of smaller projects. And that's something that's, let's say, easier to iterate on. And the second benefit that we can have if the scope gets smaller is trying to separate the questions, the sub-questions that we solve, and share them with a larger number of users. And so that's something that, for instance, can help increase the collaborative surface, sharing more sub-projects on GitHub, and then also consuming more sub-projects from GitHub to try to get more eyeballs on the same pieces of code, and that will also help, for instance, get something more reliable. Perhaps more importantly, I mean, it's not only about the research and making projects that look good. It's also about the incentives. So when you have big humanoid robots, for instance, we were always afraid of breaking the big humanoid robots because it was complex. It's not only a complex system, it's also complex to repair. And it's also quite heavy. So if it falls on you, I mean, you're probably going to survive it, but it's still kind of impressive. If we make robots smaller and more focused on the questions that we study, we also get, as a matter of fact, less afraid to break them, or less afraid to be broken by them if if they fall on you or something. So Upkie here is 5 kilograms. You don't need a crane to manipulate it. You can just leave it roam in a room, and after a while, you even get used to having the robot falling from time to time. The first iterations, of course, a few things break and you iterate in 3D printing, but after a while, it becomes more natural to just pick it up by hand, put it somewhere, start to test whatever you're going to test, and this is actually, I believe, quite important to be more efficient because we are less afraid to use our robots and we spend more time with them. Okay, so that was the case for building robots using the new, let's say, newly available actuators and 3D printers, etc. So that's more for the hardware. Now I would like to switch to the software and raise a couple of more points. And then after that, if you are interested, we can spend more time in discussion together. So yeah, my second point would be about motion control software. So, back to basics, just stating the obvious, but motion control software, what is it that we do when we develop such software? So first, motion control is about making the robot move. That's the motion part. And then we make it move because we are trying to make it achieve some tasks. So that's going to be the control part. And the task could be, range from locomotion, manipulation, folding, whatever we want to do. And we can all phrase them intuitively in our minds. But a key part of the work that we do when we translate this into software is actually to take it out of the human, easily understandable way and formulate it in the cold way of task-based formulation and control, or Lie algebra. So for instance, locomotion becomes changing the position of the floating base with respect to an inertial frame of reference. But we have to do that because we try to do software for it. So motion control software is software with which we implement this motion control. And part of our motion control software is specialized. So everything starting from Lie algebra to describe positions and motions of things in the world, to rigid body dynamics, so how to apply the laws of physics to make them move, but in a particular way, to physics simulators, which we use for instance, for training, and optimal control, which we use to make decisions in our robots. So some of it is specialized, although arguably optimal control is more general than robotics. But we also have usually a lot of clutter in our motion software, not clutter, but bloat, like things that we end up re-implementing just because there's no single source of truth for it, but we tend to replicate it all the time. Timers or loop frequency regulation, in my opinion, is one of them. Logging and analysis of time series data is super important for us, but it's something more general. People in data science have also great tools for it, and probably we don't use them as much as we should. Build systems, packaging, continuous integration are quite general. Like every software engineer has developed expertise around it, but we end up having or rediscovering or slowly learning to also dive our way into it. Yeah, and so a number of things are more general than robotics, is what I want to say. Today, I'd like us to focus on motion control software for research projects in particular, which may have some differences with motion control software as you would do it in production, for instance. And I think for research in particular, we don't have huge teams of engineers in a single place, all collaborating in the same environment. So we want to leverage the power of collaboration at a broader scale. And so today I'd like us to focus on social networking via GitHub as a collaborative environment. That's one. And the second one is the importance of packaging system to share our software, to make it more easy for other people to install our software and use it. And I've been talking quite a lot already, so I'll give you a quick break with some interludes where we can run some Python code. And if you're interested, please fire up a Python terminal next to your window and run the code at the same time. I will also do that while talking, just to show you a couple of things that you can find on GitHub. I mean, it's not purely advertisements of these projects in particular. It's more about it could be any project, but it's more about an ideal that we make things easier to grab and easier to share with other groups for reproducibility. So one of them is just loading robot descriptions. Where is my URDF, basically? And a lot of the ugly code or the non-generic code that we see in softwares is getting the path to the URDF, getting the path to the proper folders, and then getting things to stitching these paths and then loading the URDF. So one thing we can do in Python is make a kind of a diary of URDF models that people have already put on GitHub, and then just read from this diary and get a URDF description. So here I'm going to load the one for Upkie because the code from the slides is for Upkie, but feel free to pick any one you want. So the project is called robotdescriptions.py on GitHub, and from this page, you have a list of descriptions. So you can pick whatever you'd like. Mobile manipulator, humanoid, pick Jackson. It's a big complex one, very colorful. Pick whatever you want. And then you can continue running the code with the description that you picked. So, and we are going to visualize a bit, if time allows it. So here there's still a bit too much code in my opinion, but it's kind of step by step, opening a 3D scene. And loading the meshes and then displaying the robot in a given configuration with Pinocchio. So this one uses Pinocchio, but there are other backends that you can use. For instance, Mujoko, if you want to load a Mujoko environment. All right, that's pretty much it. That's one interlude. We can continue that later. So yeah, so here I fired some code in Python, but as you know, one thing that's often critical for us in robotics is performance if we have some tight control loops. So we end up using multiple programming languages, and that's where the fun begins when we want these languages to interact together. So Python is fantastic for a number of reasons, introspection being one of them. There was a question for me as to how we can run real-time code on Python, which we're going to come back to. And Python is also great for packaging. But for performance, we tend to use C++ these days. There are some upcoming alternatives like Rust or Julia that could be interesting. And thank God C++ has a type system, so that's already helpful. But it also has some problems related to complexity, how long it takes sometimes to build big projects, and the lack of packaging system. So when we try to use C++ and Python together, a common approach is to use bindings. So you make these intermediate files where you describe how your C++ functions can be used in Python, for instance. Or it has also been done in OpenHRP, for instance, OpenRTM, or other middleware to use interface description languages. So again, one file and a specified format for describing your API and allowing Python code to call C++ functions. I think we can do better for prototyping, especially if we want to avoid overheads and the complexity that makes it tedious to change stuff. So one thing I'm proposing today, and I'll be very happy to get your feedback on it, is something much dirtier. That's looking at our code and saying, well, at some stage, we're probably going to have a decoupling. So we're going to have a cascade of two controllers, one of them that's going to run a little slower, and one of them that's going to run at, let's say, a kilohertz, because usually kilohertz is the frequency that we used to do, for instance, torque control in torque-controlled actuators. So we could have a C++ process running faster at this frequency, fast frequency, and then being interacting with a Python process running slower at a, let's say, a low frequency controller. And then as we've seen, and is very common in reinforcement learning, to have a state observation action loop. I mean, it's also standard in control theory. We can implement this loop by just saying we're going to share dictionaries. And we're going to deserialize and reserialize the data. So that's going to be some overhead for the program. But then it's not overhead for the programmer, because we can change the API anytime we want. And yes, it's dirty, but it's also very fast to iterate on. And so that's one project that's called VULP, where, well, basically what VULP is proposing is a very small IPC protocol, inter-process communication protocol, with a small state machine, and it's just made to exchange dictionaries between a fast program and a slower program. So the one that sends the action and the one that sends observations. And so this is designed so that we start doing all the things that we want to do in Python. And then if we find that at some point we need to switch to C++, because one loop has to run fast. For instance, it's force control, and in this particular experiment, we need to have reactivity to walking on a seesaw or something that's where the environment changes very fast. Then we can easily switch to C++, and we don't have to break things apart and end up with a spaghetti connections where we need to change the code at 40 different places to make it work. And also this, well, it's not an added benefit, but we always want to have a simulation real switch, which we can do on the Python side. It's also provided by VOOP, but yeah, that's something else. And we'll see why this is suited to balancing in particular. So if you're interested, because VOOP uses Bazel as a build system, you can actually run it again from a terminal. If you're on Linux, I haven't tried it on other operating systems. You just need to clone a repository, and then you don't need to install anything. You can just run Bazel from the tools folder of the repository and ask it to run. So here it's called the Blue Balancer, which is going to fire up a simulator and a robot controller balancing the wheel biped with a very simple PD controller on the wheels. Careful, if you run that, it's going to download and build everything. So it's gonna take a while the first time, but it should work as a one-liner. So depending on the time we have, okay, I might have to go a bit fast on that if we want to have time for questions. But one question that I threw in the air was about, can we make real-time systems with Python? And so just recalling, but real-time means that our system, our code, responds to events within a predictable time. So when we have a loop, basically, if it executes at 200 Hertz, then we have a steady 200 Hertz execution. And we don't have from time to time that the loops takes, let's say, 50 milliseconds instead of 5 milliseconds. And that's something that we should be wary of, especially if we use Python, because, for example, it's garbage collected. So you might have a garbage collector that fires up once in a while and then ends up, blocking everything. And so I didn't have a preconception on that. So I just run an experiment where we have a Python process running at 200 Hertz on a Raspberry Pi. So Raspberry Pi is the computer onboard Upkie, and it's not a very strong CPU. It's 1.5 gigahertz, and it has you have 4 cores, and that's it. Not running any of the preempt real-time patches or things that we usually do with in-motion control systems. And but here it's not using any of that. It's just running a Python on a separate core with CPU isolation, and the Python is doing the heavy lifting in terms of computation. So it's doing inverse kinematics using quadratic programming optimization. It's doing the balance control. It's taking care of most of the code. And then we just have a very stupid spine that relays the Python actions directly to the motor controllers on the CAN bus. So it's a standard position, velocity, torque commands. And it's also running a few state observers, but they are like very simple. We could also put them in Python. It's not about performance. And here, what you can see basically, well, to my surprise, was that Python is well, at least it's competitive. It's more reliable in the sense that the variability, so the scales on the two plots are the same. Both are showing the period of the loops running in each process. On top, you have Python, and in the bottom, you have C++, the spine, running at kilohertz. And so the spine has kind of a 5% variability, and you can see on the robot, this is a 40-second sample of the robot just balancing somewhere. And yeah, the spine has some 5% variability, and the Python is actually a very neat in terms of timing. And you do get occasionally a few 5% up, 5% down, but otherwise it's super reliable. Despite running a QP optimization, I think this one is quad prog and a number of things. You have more details in the links, and you can get them from the slides if you want. All right, that was a lot of talking again. Given the time, I am not going to run the Python code with you. Sorry for that. But just giving you a quick overview of sharing. This one is sharing the inverse kinematics as a Python package. And so it's also based on Pinocchio. So all the rigid body spatial vector algebra, sorry, is already done in Pinocchio. This one is a Python module that defines the concept of task. Put a body somewhere in space with position and orientation costs. We can use Meshcat and a little bit of overlay on Meshcat to display the frames and have our targets move around. And then we can have a rate limited loop that updates our targets and have the robot track it by inverse kinematics. So yeah, we can discuss that a little bit more afterwards if you're interested. Just mentioning that IK by numerical optimization has solved a lot of the interesting cases that we want to solve in practice. One property that's important is that tasks can become unfeasible and feasible over time. So exit the feasibility workspace, then have your task keep evolving, and then re-enter feasibility elsewhere. So you want to avoid the jumps and you want to keep your inverse kinematics continuous. But we know how to do that mostly. I would say the Achilles heel today is the tasks that are feasible, but exactly at the limit of feasibility workspace. If you have some ideas or insights into how to solve this, definitely, I would be interested. I think this is still kind of a bugging question. Anyway, I'm mentioning inverse kinematics because both like humanoid LIPM walking controllers or the controllers running on Upkie use such inverse kinematics. And well, given the time, let's go very fast on balance control, and we can come back to it later if you're interested. But basically, balance control is important for robots in the real world because we never track the trajectories perfectly. And I'm assuming I've seen on iCub that you used you've tried different kinds of balance control, and there was a nice comparison also of different techniques. Here, I want to tell you a bit more in particular about DCM-based feedback for balance control. So if we have our robot working in the linear inverted pendulum mode, so the most explored way, a centroidal model to do walking, we can decompose this second order model into a simpler first order model with only the divergent components called the DCM. And we can regulate this DCM by force control if we have a big biped, for instance, moving the ZMP around to bring the DCM back into the desired position. And this helps us balance and recover from disturbances. If we are looking at Upkie, it's basically the same framework, just that your wheels move on the ground and you have velocity control, for instance, on the wheels. But the idea is the same, and you're going to move the wheel where you want the ZMP to be to balance the robot. The point I'd like to highlight is that there is this very interesting paper from Nahuel Villa, Johannes Engelsberger, and Pierre-Brice Vibert about the sensitivity of these balance controllers to the sampling period. And the result that they came up with is that if you look at the ZMP tracking error during your control, it is actually not impacted by your sampling period, meaning that you can reduce the frequency of your control loop as long as your period is below a maximum period or your frequency is above a minimum frequency. And if we compute the values for these limit periods, they are actually quite large. So for HRP4, with the lip walking controller I mentioned before, we have a minimum control frequency of 16 Hertz or a period of 60 milliseconds. And that's way above what we do in practice. And so what this suggests, and one avenue to explore further, is that balance control is actually a low frequency task. So we could move it to Python, basically, and out of C++. So the paper has both theoretical contribution, but also experimental validation on Toro, reducing the sampling period, increasing the period to as much as 120 milliseconds, and the robot was still walking around, which I highly recommend this work. I think this is super interesting. We're going to skip through force control. I just want to make a point that basically, with inverse dynamics control, we had to have the whole QP base running at high frequency if we want to send joint torques to our robots for balancing. With inverse kinematics, we could have, for instance, the balance control running at a lower frequency, although in the case of this implementation in C++, everything was in C++ for HRP4. And I'm skipping some details. You can take a look. There is also a blog post on my website if you're interested into the potential connection between how we design contact flexibility and the sampling period. And what I wanted to say here, but you saw me coming, is that on Upkie, the full pipeline is basically in Python. So the balance control and the inverse kinematics are all running at a lower frequency. And indeed, there's no much problem. So the first version of the controller was at 400 Hertz. And then one day I switched it to 200 Hertz, and there was not much of a hassle, not a lot of parameters to reconfigure or these kind of things. All right, let me wrap this up so we have time to talk. So I wanted to make 3 points with you today. The first one is that it has become easier to build our own dedicated hardware for a fraction of the price of the huge robots that we worked with before, the big robots. And these robots are homemade. They can be made in a lab, but they could also be made in any room where you can fit a 3D printer and a bunch of tools, probably shelves, etc. And that's super interesting because we can make robots that we're not afraid to break, that are smaller and more dedicated to the tasks that we want to study. My second point was about software, and especially software for research projects. So I try to make the case that we collaborate as much as we can on GitHub as a way to alleviate the lack of huge teams of engineers, and use C++ when needed, and when it's not needed, aim as much as we can for a high-level language. And so with particular case of C++ and Python, we've seen VULP, which is one way to have this kind of decoupling, but without bindings, and rather implementing action observation loop by IPC with dictionaries. And one enabler for that is that Python can perform real-timely, and it actually got better even with 3.11. Python actually got faster in recent iterations. So we can use it at low frequency. And actually several tasks that we tend to implement. Many works do very fast balancing, faster and faster MPC, for instance, but that might not be needed for running on real robots, because balancing, in the case of DCM-based balancing, is actually low frequency, for instance. All right, that's it. Thanks a lot for your attention, and I'll be looking forward to the discussion with you guys. Thank you.
Thank you very much, Stéphane, for the presentation and overview. So I don't know if there is any question from the audience. So do not hesitate to raise your hand and speak aloud. Check.
So I have a question.
Sure.
So Stéphane, I had already used one of your repositories, the robot description one. First of all, I will say thank you. I mean, this was something that somebody had to do a long time ago. So this actually solves a lot of problems for actually testing something rapidly. So I really like this. I didn't knew that you had more repositories and that you had this whole project for standardizing developing in robotics. I do have a question. Do you plan, or do you already have some sort of standardization in the way you let's say communicate between software libraries like Pinocchio and then the simulators, for example, I don't know, biped or Muyoko. So normally what occurs is that the controller runs with Pinocchio, but these two softwares have different, let's say, ways of describing the robot and so do you plan or do you have already some standardization of this?
No, well, I see exactly what you're pointing at, and it's true that it's a real problem when you have the simulator, for instance, ANYmal rigid body dynamics library not having the same API, the same conventions. I cannot standardize alone, and that's not the goal at all. So VULP, for instance, here. VULP is a proposal in the sense that this is software that was needed in some projects, and then tries to be as small as possible, and see, let's say, if this question is worth isolating and can be reused, then we can, either use it directly or just take the idea that's useful and make another project out of it. But it's not an aim for standardization. Standardization would be, we would need a discussion space also to really bring things together. So here what VULP does, and it's not helping, it's not addressing the question that you're pointing at, it just provides a real robot / simulation switch. So which is what you can find in other motion control software. Basically, let's see, when you won't see it with a one-liner, but when you want to run in simulation, you just start a simulation spine, and then you run your Python agent. You don't need to change anything from the Python side. You run exactly the same script, and then when you want to run on the real robot, then instead of the simulation spine, you just switch to the electronics, the spine that talks to the electronics via the API, and there is it's just one submodule that you change, and the Python code is always the same and interacts with the spine. So this is a standard simulation to real robot switch, and it's not taking care of converting all the representations between your simulator and your library. There could be a need for that. I would actually be interested in following if we develop some kind of a let's say a POC or some project around it, but I haven't seen that so far.
Awesome, thanks. I know that the people from CNSR have some sort of communication between Pinocchio and PyBullet, which I am actually using and editing constantly.
Okay. Okay. How is it called?
Let me.
I can look it up later if you say so.
The class is called PinBullet Grapper, but I've already forgot from which package I originally took it.
Okay, I'll look it up later. Thanks.
Perfect.
Okay, I think that Silvio wants to intervene. Silvio?
So, first of all, Stéphane, thanks a lot for the presentation. It's been really nice. So my question is regarding you point out packaging technologies as one of the key enablers of collaboration, and I really totally agree. And people that work with me probably know that I totally agree. And I was wondering if you could comment, if I can get your opinion on the state of packaging tools or techniques, or let's say best practice for what regards C++, because for Python there is a lot of let's say best practice. For C++, I think there is more or less agreement again between people working in robotics, and I think that also you with Valp choose a way of, let's say, distributing the software that may be innovative and convenient through Bazel, but can also be problematic if you don't use Bazel. So I was just curious about that, because you identify packaging as a struggle, and that's not so common, because a lot of people say, oh, okay, there are these 25 lines of commands to install the software just with this version of the dependency. That's perfect. Instead, you identify, so I was wondering.
Yeah. I'm exploring this question too, so definitely I don't have, I haven't found a satisfactory answer to the problem of distributing C++ software. That's also one of the reasons that prompted me to try out Bazel, because, you know, it's like new kid in town, and they are proposing a few things that are quite fresh. So I wanted to try it out as opposed to CMake or what I used before with Ross, Catkin, for instance. And it's probably not the end of the road. I would say Bazel is also shifting, like is also shifting quite a lot. I'm not sure how to, you know, I'm pretty sure I cannot give you a satisfactory answer, but Bazel is something I've been very satisfied with from the perspective of using software. So if it would become more standard, I think it would be a net good compared to using CMake, for instance. That's my guess. That's my feeling. Just because CMake has evolved over the years, but I find that it's still, you know, it hasn't evolved. When I see the state of where we are today when using CMake projects, I feel that it hasn't lived up to the expectations of becoming a proper distribution system. Bazel is a bit rougher when you start it to use it. It's very convenient to. It's quite easy to get other projects in your Bazel project. That's why, for instance, you get the one-liner here, even though it's using Bullet, so it's going to pull Bullet. There is no Bazel distribution of Bullet, but Bullet is structured in a way that, you know, once you know where the headers are and the C++ files are, you just list them all and tell to Bazel, build everything, and it just builds. And you don't need to, or probably you specify 1 or 2 compilation flags, and that's it. So from that perspective, I feel it's very powerful, and it solves a number of things that I believe CMake is lower level in a way, so it didn't solve very well. But then you pointed out the question that what happens to do if you develop something inside Bazel and then all the other users around you are not using it. And to that, I don't have a satisfactory answer. I tried the new kid in town, and I think that kid has a number of points that are pretty good. So, you know, it's worth considering. And then, as far as I know, the latest iteration of Bazel, they are moving to something that looks like what Conda has done with the recipes, stage recipes. So something more centralized in terms of having packages, because the initial iterations of Bazel is like you can pull software from anywhere, from a USB key, from GitHub. It will pull anything. But they are moving towards something more package-like. So my current guess is I will keep following what happens with Bazel, because that might, you know, that might live up to higher expectations than when we have with CMake. But the struggle is still going on, and I don't think the battle is not over yet.
Okay, thanks a lot.
Sure.
I don't know if there is any other question, curiosity for Stéphane. Yes, Stefano.
So again, thank you very much for the talk. It was very interesting, very let's say close to the real work. So thank you very much for that. So it was I was thinking about one of the last few things that you said about the controller frequency for balancing. Mm-hmm. So I was wondering whether what's your take regarding external disturbances? So what if we actually lower down the controller frequency too much, and then we kind of lose? Is there the chance that we lose something with respect to the robustness or to external disturbances, for example? What's your take on that?
Sure. Yes, we will lose. Well, the question is what we lose. So how do you? We will lose something when we lower the sampling frequency, and that basically depends on the spec. So, if you think of, if you remember the one of the gymnastic videos of Atlas where it was doing a salto and then landing on the ground, if you look at the feet, you will see the feet vibrate very fast after the landing. And so you can imagine that, I mean, this could be due to either the robot or the ground, but if your specification for an external disturbance is the ground is shaking at 10,000 hertz with some amplitude, then you would definitely lose something. I mean, you're not going to react to such a specification. But if your specification is the robot is resisting pushes against humans or static obstacles, then you can have a more precise idea of I mean, then the frequency of your disturbances will be lower, and then you will still see them in your controller. So to me, there is this connection to be made between what's your specification for the external disturbances that you want to be able to resist. And then once you have an ID, once you have this specification, you can map it to your balance control, to your sampling period. So in this paper that you see on the slide, you will have the slides afterwards. There is actually a modeling. So there is a modeling step to establish the result and the independence on the independence of the ZMP tracking error from the sampling frequency below this threshold. And if I remember correctly, but we would need to check the paper, inside this, the external disturbance is modeled as basically a box of ZMP disturbances that you can get at each time step. So I think from their analysis, it shouldn't be too hard to come up with your own custom model of what are the disturbances that I want to resist, map them to this ZMP box, or maybe you can extend the analysis to the mapping, and then you can see the effect on the sampling frequency. But yeah, I mean, in summary, my 2 cents would be start from your specification for the disturbances, and then follow the pipeline to see how it propagates to the sampling period or not. Does that answer your question?
Absolutely. Thanks a lot.
Cool.
Okay, so I don't know if there is any other question for Stéphane. Okay, so last question I wanted to ask you, Stéphane. So you somehow highlighted a lot the importance of iterating hardware somehow quickly, no? Also to understand what is the best hardware given the task. You advocate the fact of somehow using the, I don't know, the specific hardware for balancing or for walking and etc. So I just wanted to know, I mean, as a research client, we're trying to do some effort in iterating actually this idea in simulation rather than the entire building process. So what was your intake about this somehow attempt of iterating in simulation, and also clearly this calls for sim to real questions. But anyways, I wanted to have your opinion on this.
Yeah. Well, yes. Okay. I see. It's indeed. I didn't spend a lot of time on that, but you're absolutely right that there is a cursor to decide how much you design in sim versus real hardware. I tend to be, but that's more opinion. I don't have a lot of facts to support that opinion, but I tend to be on the side of spending more time on hardware when you want to develop a controller. I mean, probably if you're not sure. So in the case of balancing, we already have preconceived answers to what are the different types of balancing robots. We might actually have missed some, but it's not like, for instance, some very alien task where we would have no idea. Do we need to put 2 arms or 3 arms, or what kind of morphologies could we take, and then we would go. It would be interesting to explore robot shapes in simulation before building them. I have one practical example of that actually. Before that, when I was in the Nakamura lab, we built a tendon-driven 5-finger hand with opposable thumb, and then you have a lot of tendons in the hand. And one question was, how are you going to do the routing? You know, how many tendons, but also where do you put the pulleys so that you get a routing that's optimal in some way? And for that question, it was well enough defined that we used optimization and simulation before building the thing. So that made sense to me at the point. But from a control perspective, I tend to believe we should spend more time with hardware than we do in sim. And that also can help crossing the sim to real gap, which you mentioned, in the sense that if for a particular task you have accumulated a lot of time running on the real hardware, even if you're running with some teacher controllers, in a sense, you can also save that data because the data is also precious. And that's a whole question that we didn't discuss in today's presentation, but that other fields and that machine learning and people working in deep learning have solved already is how do you collect efficiently the data from all your experiments and how can you reuse it in the future? You know, if you have a data store of all the previous runs of your balancing controllers, even with various controllers, they can be used, for instance, in an offline reinforcement learning setting to produce new controllers or to iterate. And so I am very interested on that side of the spectrum where we spend more time with the hardware. And then if you start to unroll this line of reasoning, you want to spend more time with the hardware. So the hardware needs to be, you know, to have a bigger uptime than what we had with the big robots or the previous generation of robots. And then it might also fall more. So you want to be able to repair them more, etc., etc. So that's kind of this line of reasoning leads you, in my opinion, to homemade or rapid prototyping of robots, basically. Does that start to answer your question, or you see it's more opinion than fact? But
But actually, it was just to know your opinion. There are a lot of open questions, so we still have to find out how to somehow answer them. And there will be people more on hardware and more on simulation. Then somehow at a certain point we will converge.
Hopefully, yes.
Hopefully, yeah. Okay, so I don't know if there is any other question for Stéphane. Okay, no. So Stéphane, I wanted to ask you once again for this great talk. And well, at this point, somehow we can close the session. Just as a personal note, thank you very much, Stéphane. It's been really a pleasure to see you again, and let's hope to cross each other in one of the next conferences.
Sure. Same here. Thanks a lot, guys. I enjoyed a lot talking with you all. Thanks.
Thank you.
Have a nice one. Bye.
Bye, Stéphane.
Ciao.
Bye-bye.